It's about Bio-CCS, negative emissions, and why should we be interested right now? What has changed? Myself, Antti Arasto, and Kristin Onarheim, both from VTT, will be presenting. I will start and Kristin will continue. And because of excessive amount of material that we have, we thought that the easiest way to deal with questions is that if you come up with a question, use the chat box or the conversation box, type it down there, and then at the end we'll tackle all the questions. So let's get started. Bio-CCS 101, and why should we be interested right now? I'll start by introducing Bio-CCS once again. Most of the attendees have probably heard something about the topic, but also trying to address a bit what is different now, and this is especially from the Finnish perspective. First of all, I've always started by saying that Bio-CCS is more a systemic issue than it is a technical, and I'll explain that a bit later. But why Bio-CCS? The beauty of it is that negative emissions, meaning removing CO2 from the atmosphere, has the ability to offset emissions over sectors and time. So this is why Bio-CCS, or some want to call it BECCS, is in the discussions currently so much. Main reason, I just closed the window. Main reason why the tone of voice has been changed since last fall is, of course, IPCC SR 15. A special report that explains reasoning and consequences of reaching 1.5 degree climate warming target instead of a 2 degree target. And not going into detail of that report or IPCC work, that's a webinar of its own. But even the 0.5 degrees Celsius difference sounds like a minor thing. It's actually changing the ambition level tremendously. And one of the, here, as many of the actors around climate change, IPCC also works with scenarios. Here you can see different scenario pathways how this 1.5 degree target could be achieved. And one thing to notice from all of these is that all of these pathways use carbon dioxide removal. Whatever the technology or the means to remove CO2 from the atmosphere, it is in all of these scenarios. And also this is intuitively quite rational, but the more emission reductions are delayed, the more CO2 removal from the atmosphere is needed. Now let's take a bit closer look. The general conclusion is that in order to limit the global warming to below 2 degree levels, net zero emissions should be reached by mid-century. Net zero here means that we do not emit more CO2 to the atmosphere than is withdrawn either by natural phenomena or by human technologies. So, and as I said, all of these scenarios need carbon dioxide removal in order to reach 1.5. The balance between CO2 removal based on land use changes, forestation, changes in agriculture, and what can be done by these technical solutions called Bio-CCS, the balance varies, but both are actually existing in all of the scenarios. And also going beyond 2050, as I said, net zero should be reached more or less by then, but soon after we would have to be carbon negative. We would still need to remove some of the CO2 that we have historically emitted to the atmosphere. And this is very different from what we've learned in previous years based on the 2-degree scenario works. Not all the scenarios did have this element, and it was more or less a minor element in most of the scenarios, whereas now the tone has changed, as you can see. Of course, this is now 50 to 100 years perspective that we are discussing the topic. Then let's go a bit into the technology then. What is Bio-CCS? Bio-CCS is of course heavily connected to biomass use. And the ability of biomass to absorb CO2. Provided that this is the biomass use is on a sustainable level from the climate perspective, when we use the biomass, at one point CO2 is generally emitted back to the atmosphere, creating a loop. And this is the basis for carbon neutrality thinking of biomass. But if we instead keep growing new biomass, but take the CO2, for example in energy production processes or whatever conversion processes that result with CO2 streams, and permanently store it underground, then on a systemic level, the net result is that we remove CO2 from the atmosphere. And this is explained with numbers in this picture. This picture concerns electricity production, but of course similar type of thinking applies to all processes using biomass as raw material. Then one aspect that I think it's worth mentioning or bringing up in the discussion of Bio-CCS is CCU, carbon capture and utilization, since it's often used in association to Bio-CCS, and these terms are misinterpreted either by purpose or by accident and confused or mixed with each other. And there's a fundamental difference between CO2 use and CO2 storage, where Bio-CCS, carbon capture and storage, results in a net negative emissions, it enables offsetting emissions across sectors and also historic emissions. It removes CO2 from the atmosphere. CCU, however, is at best carbon neutral. It is not removing at least significant amounts of CO2 from the atmosphere. There's a small climate impact based on the fact that carbon is bound to the products made of that CO2, but eventually it will be emitted back to the atmosphere. And actually the climate impact of this CO2 use is totally different, because it primarily comes from the fact that it enables new low carbon electricity to the system. It might enable indirect electrification of sectors hard to decarbonize, and it also enables low carbon electricity being a raw material instead of fossil resources. But it is not resulting in significant removal of CO2 from the atmosphere. And one fact associated to CCU is that significant amounts of electricity is needed in order to use that CO2. So even these two acronyms, CCU and CCS, they are quite similar. They have a totally different meaning and a totally different logic how they can combat climate change. They both have a role in combating climate change, but the mechanism should not be mixed. Then getting back to the Bio-CCS, so the storage story. And I've been thinking that actually implementing these kind of technologies, it's not only one technology, it's actually that the story has three different chapters. It has the aspect of biomass supply. As I said, we need to be on a sustainable level, and we need to be using the biomass raw material that is scarce as wisely as possible. That leads to the second step, that actually, as I see this, the applications of Bio-CCS, so capturing and storing biogenic CO2, should be connected to the market-driven use of biomass, meaning that biomass is used where it is at its best. And then when it results in CO2 emissions, then of course it makes sense to capture those and store. But this limits the portfolio of both sectors and plants that we can apply this technology in. And finally, the third chapter of deploying this technology is associated to CCS. What is needed in the capture, transport and storage value chain and technology development pathway to go further? As my opinion on this is that Bio-CCS is not the primary driver for CCS. Instead, conventional fossil CCS is more or less a prerequisite enabling also Bio-CCS. And then the final slide of my part of the presentation is how this concerns Finland and what is changed in Finland. Apologies for English speakers because of the Finnish expressions in the slide, but this slide shows scenario work that was done and published this spring. It's part of the official climate and energy strategy work in Finland, and it concerns how Finland can transform to carbon neutral. It's also based on scenario works, so different pre-assumptions, different restrictions in the model. However, also in Finland, where you might already know that there's a lot of carbon neutral electricity and energy in general already available, we would still end up deploying Bio-CCS, so removing CO2 from the atmosphere, offsetting emissions across sectors, if the lowest cost pathways from the societal perspective were to be followed. This is due to the fact that we still have CO2 emitting industry in Finland, and we also have transportation and agricultural sectors that remain CO2 emitters. And therefore, in certain sectors, we might have to overdo things in order to retain some of these critical sectors still in Finland. So, Bio-CCS is visible in these scenarios. It's visible only, let's say, after 2040 or after 2030, coming to significant amounts only by 2040. But now world has changed. This work was started also before the IPCC 1.5 degree report. So the target setting of this was 2 degrees. So what we are aiming is even tighter from now on. And the government plan that was recently published also states that Finland targets to be carbon neutral by 2035. And both of these factors are doing two things. They are stressing the importance of CO2 removal, so making the relative importance higher. I can't say by numbers yet, but also it's making the need coming way before than 2040. So we would need to deploy these technologies faster. And this is why right now we would like to take a closer look at what is possible in Finland. And as a small advertisement, we are of course currently doing our own 1.5 degree scenarios also for Finland. However, they are not ready yet, so stay tuned for those. But for more detailed possibilities in Finland, I would now like to give the floor to Kristin. And let's see if my computer skills are sufficient to give rights to Kristin.
Okay, hello everyone, and welcome also on my behalf. I don't seem to be able to change the slides, Antti.
Is it working now, Kristin?
No.
Should you open the presentation from your computer in order to avoid the next slide, please? Sentence over and over again.
Yeah. Okay, so I think now it should be working.
Yes.
Yeah, good. As I said, welcome also on my behalf. And as Antti said, I'll tell a little bit what's going on right now and also dig a little deeper into the technology side and the possibilities for Finland. Okay, here we go. So this is an overview of the current status of CCS. So on the left-hand side, we have large-scale facilities in operation. And on the right-hand side, we have pilot and demonstration plants. And as you probably noticed, most of the activity is concentrated in North America, Europe, and China. The largest operating plants today are the Century plant in Texas, capturing 8.4 million tons per year from natural gas treatment. The CO2 captured here is used in enhanced oil recovery operations. Also, the Chute Creek gas processing plant in Wyoming, USA, captures around 7 million tons per year, also that for enhanced oil recovery. Significant Bio-CCS plants include the Illinois ethanol plant, capturing around 1 million tons per year via compression and dehydration. And this CO2 is actually geologically stored. So they are creating negative emissions. And closer to ourselves, we have the Norwegian Sleipner platform, capturing 1 million tons CO2 per year from natural gas processing. And this facility was the first in the world to inject CO2 into dedicated geological storage. Also, the Norwegian Snøhvit facility in northern Norway injects CO2 from natural gas processing to an offshore storage reservoir. So when we look at the Nordic countries and the global status on Bio-CCS, we see that specifically Norway and Sweden are active. Norway has committed to being climate neutral by 2050. And as a petroleum nation, Norway has more than 20 years experience with CO2 storage and CCS. And CCS is actually one of the government's 5 prioritized areas for enhanced national climate action. And the ambition of the government is to realize a full-scale demonstration project for CCS. And this full-scale project is one of the first industrial CCS projects to develop actually an open access infrastructure with the intent and capacity to store CO2 from across the European continent. In this full-scale project, CO2 will be captured from the Norcem cement plant on the south coast and from the waste-to-energy plant at Klemetsrud in Oslo. And this will be transported by ship to an onshore hub at the west coast, and then it will be pumped via pipeline to the storage formation in the North Sea. So the total yearly CO2 capture will be around 800,000 tons. It's based on amine scrubbing technology, and half of this CO2 is from the waste-to-energy plant, which will be a Bio-CCS facility. And the project is currently in the FEED study phase, and it is expected that operation will start by 2023, maybe 2024. On the Swedish side, Sweden has committed to ensure zero net emissions of greenhouse gases by 2045, and after that to achieve negative emissions. So Bio-CCS is one of the main keys to reach these climate targets, and Sweden has already demonstrated CO2 capture from a combined heat and power plant by Fortum, and Vattenfall has demonstrated carbon capture with oxy-fuel technology. Now the Swedish oil refiner Preem is currently aiming to build a full-scale CCS facility by 2025, and take advantage of the storage infrastructure established by the Norwegian full-scale project. So on the Bio-CCS side, Stockholm Exergi is installing a new test facility for BECCS in one of their CHP plants. This facility will, according to plan, go online in October, and the aim is to test CO2 capture from biofuels, and the facility will only capture around 700 tons per day, which will be released. But if there is a financing possibility after the pilot test, they will either scale the plant up to demonstration capacity or even install a full-scale facility by 2025. And again, the CO2 is planned to be pumped into the Norwegian full-scale project. When it comes to Finland, Finland has actually one of the most ambitious climate goals nowadays, committing to achieve zero net emissions already by 2035, which is only 16 years ahead. The government in Finland released their new government plan actually last Monday, and critical to reach this target is bio and circular economies, capture and reuse of CO2, and development of processes using CO2 as feedstock. So if we take a more global perspective on Bio-CCS, the UK government has recognized the crucial role of CCS in order to reach 80% greenhouse gas reductions. And one of the aim is to commission the first CCUS facility by the mid-2020s. The Drax power station is in the process of converting their coal-based power boilers into biomass-based boilers, and Drax currently runs a Bio-CCS pilot project, and they capture around 1 ton biogenic CO2 per day. This CO2 is not stored, but Drax is cooperating with Equinor from Norway and National Grid Ventures to scale up the existing pilot plant and create the world's first carbon negative power station. And the timescale for that is somewhere in the 2020s. And the Netherlands have committed to a 49% reduction of greenhouse gas emissions by 2030, and to increase this to 95% by 2050. And CCS plays a key role in reaching this target, and the aim is to capture and permanently store 20 million tons CO2 per year by 2030. Around 2 million tons of this CO2 is expected to originate from Bio-CCS installation, mainly in connection with waste-to-energy plants. And a couple of months back, the Twente waste-to-energy plant in Hengelo in the Netherlands, they announced that they are actually implementing a CO2 capture process to capture 100,000 tons CO2 per year. And this plant will be in operation by 2021. And the largest Bio-CCS facility to date is the CO2 capture plant at the Archer Daniel Midland's first generation corn to ethanol plant in Decatur in Illinois. I mentioned it briefly earlier. And the CO2, as I said, is permanently stored in a nearby saline aquifer. And this is the first project in the world to apply Bio-CCS on biofuels production and generating negative emissions. And also the Archelon, Bonanza and the Husky Energy facilities are similar processes with corn to ethanol, but in these cases CO2 is used for enhanced oil recovery, so it's not permanently stored. And some of these plants have actually been operating for 10 years, more than 10 years already. And in Japan, Toshiba is installing a 500 tons per day capture unit from a biomass fuel power station. And this plant is expected to be operational sometime next year. So we have three main types of CO2 capture technologies. We have post-combustion, pre-combustion and oxy-combustion, under which we also have different processes. And all these technologies are equally applicable for capturing biogenic CO2. And the most common capture technology is post-combustion capture. This is a commercial process that has been used, for instance, in natural gas sweetening for decades already. And in the next slides, I'll walk you quickly through the main principle of each of these technologies. So in post-combustion, we actually refer to capture of CO2 from the flue gas after combustion. And the majority of post-combustion facilities are based on chemical absorption with an amine solvent. After removing ash and sulfur components, the flue gas is fed into a CO2 absorber, where the gas phase contacts with a liquid solvent. And the amine then binds with the CO2, which means that the CO2 is extracted from the absorber in liquid phase, and the rest of the flue gas is vented. And the CO2-rich solvent is heated up in a stripper or a regenerator, and then the CO2 is released and the solvent is regenerated. And the captured CO2 is dehydrated and compressed for transport and storage. This technology uses around 3 megajoules per kilo captured CO2 in the form of low pressure steam, so it does pose a certain energy penalty on the main process. Also, electric power is required for the CO2 compression. And this technology is preferable for gas streams where the CO2 partial pressure is rather low. If we look at pre-combustion capture, here the fuel is converted into partially oxidized syngas through gasification. Ash is removed from the syngas. Syngas is then shifted to increase the hydrogen concentration. And after the shift reactor, sulfur components are removed and the CO2-rich syngas enters a CO2 absorber. And because the syngas is often at a higher pressure when it enters the CO2 absorber, this technology favors physical absorption instead of chemical absorption, which is more common in post-combustion capture. And oxycombustion is combustion with pure oxygen instead of air. And the result is a flue gas that consists mainly of CO2 and water. This simplifies the CO2 capture as there is no need for a specific capture unit. Instead, the CO2 only needs to be compressed and dehydrated before transport and storage. So this slide gives an estimate of the potential for Bio-CCS in Finland toward 2025. And the chart only shows the installations with potential to use biomass and those that have potential to install Bio-CCS. So fossil installations are not shown. On the x-axis, we have the amount of avoided CO2. And on the y-axis, we have the cost of avoided CO2 and the gigawatt hour per year on the bottom line here. They show the total thermal power available from the bio-based sectors in Finland. So the green bars in this chart show bio-based industries and the blue bars illustrate CCS options. The green sectors already exhibit a climate benefit from using biomass even without CCS. And when we add Bio-CCS, so looking at the blue sectors, we get a double benefit, first from utilizing biomass and then from the Bio-CCS itself. And as you can see, the potential is where biomass is already in use, such as in combined heat and power facilities. And the potential naturally follows the utilization rate of biomass. So in Finland, the greatest potential for Bio-CCS is in particular within power production. The cost increases with Bio-CCS, but apart from Bio-SNG, it doesn't significantly exceed 90 euros per ton of CO2 avoided. And the negative cost of the recovery boiler all the way on the left is due to the nature of this process, where the primary aim is to recover cooking chemicals from the pulping, and the production of energy is a secondary priority for this sector. So if we dig a little bit deeper into the different or to the main sectors with a potential for Bio-CCS in Finland and look, for instance, at biomass to liquid. Here, the integration of CCS with the production of advanced synthetic biofuels enables the production of fuels, chemicals, heat, and electricity, while we simultaneously capture CO2. And as I mentioned earlier, energy penalties of adding CCS can be prohibitive. But in the case of biofuels, both energy and capital expenses can be limited because capture of CO2 is an integral part of the basic process design. So here, for instance, we're looking at a biomass gasification process to produce liquid fuel. And natural to this process is the compression of shifted syngas, after which CO2 is removed by reaction with a physical solvent such as Selexol or Rectisol. And in this way, CO2 is actually a side stream in the existing process. And the additional investment for implementing Bio-CCS here would be from the CO2 compression, transportation and storage, and potentially also for sulfur removal if that is required. The potential of Bio-CCS for BTL essentially follows the biofuels market demand, which is then created by the RED II directive. And most of the needed component technologies are well known, and they are already widely in use in various industrial applications, but the integration of these technologies at scale has still not taken place. So another potential sector in Finland is, as I said, combined heat and power. And one potential technology, in addition to conventional Bio-CCS, is chemical looping combustion, or CLC. Said in a very simple way, this is a combustion method where we use a dual fluidized bed system. And in this way, we have one reactor for the fuel and one for the air, so that the fuel is essentially isolated from the air. And we use a metal oxide acting as a bed material, which then provides oxygen for combustion in the fuel reactor. And after reduction in the fuel reactor, the reduced metal returns to the air reactor, where it is reoxidized for another loop. And the benefit of this technology is that the exhaust gas from the fuel reactor contains more or less only CO2 with some water. So what would be needed in order to ship this CO2 off for storage is cooling and dehydration and compression for transport. So much like the gasification case in the BTL example. A CHP plant compared to a condensing power plant has a possibility for higher efficiency gains. In a condensing power plant, we'll lose some electric efficiency, but for the CHP, what is lost in electricity can be gained back in thermal output. So generally, over 90% process efficiency is achievable in CHP production if we have a large heat distribution system and relatively continuous heat consumption. In Bio-CCS processes, the utilization of relatively low temperature heat from capture plant, air separation unit, or CO2 compression units in district heating system and or in industrial applications offers significant potential to increase overall efficiency. So in both these cases, the CHP and the BTL, we could have a partial decoupling of income from electricity market if we would have a negative emission credit. So with a negative emission credit, we'd get an additional income, which means that the window of feasibility for running the plant would expand. And in that sense, it would be reasonable to assume a higher utilization rate for Bio-CCS CHP applications. So another quite potential sector in Finland is the forest industry. As we saw a couple of slides back, the forest industry has a significant potential because of the biogenic CO2 emissions. Almost 100% of the emissions are of biogenic origin. So in addition, a typical pulp mill has excess energy available to run the CO2 capture plant. And a normal pulp mill generally has three major CO2 emission sources. So we have the recovery boiler, the multi-fuel boiler, and the lime kiln. In some cases, the lime kiln may be fueled with fossil fuels. So the cost of CO2 capture from the forest industry depends quite a lot on the site configuration. And if we look at a standalone market pulp mill, we have excess steam and electricity, which can be taken advantage of. However, when we look at an integrated pulp and board mill, much of the excess steam and electricity from the pulp mill is going to be used by the board mill. In these cases, we would need to generate steam for the CO2 capture plant some other way, for instance, by adding an auxiliary boiler. And then again, this would drive up the cost of CO2 capture. Notwithstanding, if we would have a policy scenario where one is given a credit for negative CO2 emissions, this would have an adverse effect on the cost of pulp and could be a game changer. So just to show an example, here we see the effect of a negative emission credit on the cost of pulp. And we are looking at 4 different CO2 capture rate scenarios. We capture 5, 30, 50 or 90% of the total pulp mill emissions. And the reference cost of pulp mill is for a typical modern market pulp mill without CO2 capture. So, as you probably guessed, the higher the capture rate, the more severe effect it has on the price of pulp. And as soon as we get below the reference cost of pulp, we have a new business opportunity. So everything below the reference cost is an additional revenue. And if we transfer this diagram into monetary terms and consider the highest capture rate case, so 90% CO2 capture, for a mill producing around 800,000 air-dried tons per year of pulp, looking at a negative emission credit of around 65 euros per ton would give this mill an additional revenue of 121 million euros per year. And that is a significant additional revenue for this size mill. It's neither too far from the 45Q bill in the United States, which operates with a tax credit of $50 per ton stored CO2, and it is around the same cost as the CO2 captured at one of the largest facilities to date, the Petronova facility in Texas. So it's not completely unrealistic scenario. So is this even possible in Finland, and how would we transport the CO2 and where would we store it? So yes, it is possible, and CCS would significantly contribute to reducing the greenhouse gas emissions and reach the very ambitious climate targets of Finland. And as you can see from the map here, most of the potentially large CCS facilities are situated along the coastline, which facilitates transport by ship to storage sites. And we already know that there are dedicated storage sites for CO2 in the North Sea, and that the infrastructure for receiving CO2 to these formations is under development. We also know that there is a potential storage site in the Baltic Sea, which of course would be a lot closer to Finnish emission sources. However, the capacity of this formation is much more limited, and the formation itself breaks into international seawaters, so development of this site for storage will take some time. So the North Sea formations are optimally situated with short transport distance from much of Northern and Western Europe, and also from the Nordic countries, including Finland. And in connection with the Norwegian full-scale project, Norway is also looking into possibilities for importing CO2 from Europe in something called European CO2 Transport and Storage Network. Now, here would actually be a golden opportunity for Finland and for Finnish CO2 emitters to link into this infrastructure and actually be part of the development while there is still room to establish practices that will benefit Finnish industry. And one way to do this is to establish a full-scale demonstration of industrial CO2 capture and storage, like they're doing in Norway and Sweden and in the UK at the moment. So to wrap it up, Bio-CCS is the only industrial large-scale technology to date that can generate negative emissions at the scale needed to reach the climate targets. And large-scale implementation of Bio-CCS is not a technical issue, it's more a systemic issue. And Bio-CCS is, as we have heard, it's no silver bullet to our climate change challenge. And in general, it's not a solution to possible sustainability issues related to biomass. However, it does have an impact on the greenhouse gas balance of biomass use. So to wrap it all into one sentence, to secure carbon neutral Finland by 2035, which is a very, very ambitious target, technology implementations should start today. So thank you all for listening, and I'll give the scene back to Antti.
Thank you, Kristin. You can put the last slide, the one with our contacts, in case someone later on wants to ask something more.